Hello and welcome to Free Radical Substitution. Please log on to Mr. Gardner's website, which is IBDP Chemistry, Standard Level Topic 10, Organic Chemistry, Free Radical Substitution. You can have a look through the objectives here. Low reactivity of the alkanes, they either undergo combustion or free radical. Combustion equations you should be able to recite for methane, ethane, propane and butane. The only other thing they do is if you shine them with UV light, as you saw in the starter, they will explode and stimulate a chain reaction, which is fun, exciting and explosive in equal measure. So applications, so you can explain this and talk about the photochemical homolytic fission. This topic is emblazoned, ingrained with jargon words like homolytic and fission and free radical and mechanism, and I'll try and unravel some of the mystery of some of these things here today. So the reference should be made to initiation, propagation and termination steps. Yep, we got that. And free radicals are represented by a single dot. The IB like this. They like to ask you about how covalent bonds can break. So there are three ways. We can have unequal splitting. Unequal, that means one electron is transferred, either lost or gained, or shared. If it's lost or gained, it's going to be ionic, so it's producing ions, and this is heterolytic fission. Heterolytic, two different, homolytic, two the same, haha. Equal splitting produces radicals, and this is homolytic fission or homolysis. Homolysis, what a wonderful word. And this produces radicals where one electron goes to each of the species, and there's another wonderful word that we need to use, species. If several bonds break, the weakest bond is broken first, so you need to know your reactivity of your halogens. So the fluorine-chlorine bond is going to be exceptionally strong. Why? Because fluorine is the most electronegative element in the periodic table. And the bond's going to get progressively weaker between carbon and the halogen as we go down group 17. Okay. Energy required to break bonds can come from a variety of sources. For IB's intents and purposes, it is light, UV light, and I'll show you that on the mechanism when I go through it shortly. In the reaction between methane and chlorine, you can use either, but it's standard to be UV. So three different ways of splitting, we can represent them. Unequal splitting to make ions, which you are used to, where one electron is lost, that's going to form Y+, and one electron is gained, which is going to form X-. So this is standard ionic bonding. This is heterolytic fission. When we do more organic chemistry, this can happen also in organic molecules, where you get heterolytic fission between carbon and a leaving group. We're not going to do that today. Let's focus on free radical homolytic fission. That's enough for today, I think. So equal splitting produces radicals. A radical is a species, it's an element with one electron. You can have Cl with one electron, which is represented as Cl dot, as we have X dot here, or you can have alkyl group, which is a free radical, which is also represented by having one single dot, which I'll show you shortly. If several bonds are broken, it's the weakest that goes first, we've said that. Free radical properties, they are highly reactive. They don't like being in existence. They want to neutralize or quench that one electron. Is highly unstable on the species to which it is attached. Okay. So you can form them from thermal cracking. They are involved in the ozone layer. Chlorofluorocarbons are a potent ozone layer depleter. That's not part of this video. We'll do that in a separate video. So what happens when we react chlorine with methane? The reagents, we need UV light or sunlight. Sunlight is good. And what happens overall? Here's the equation. Methane plus chlorine makes hydrogen chloride plus chloromethane. It can go on to substitute further to make the dichloro, the trichloro, and the tetrachloromethane. These radicals are so reactive, they just don't do anything to quench that one formal electron. Now, mechanism. This is going to be your first mechanism. Think of a mechanism as a story. It's the story of what happens to get from your reactants to your products. We want to know as chemists what's going on behind that. So the mechanism that we're going to learn today is free radical substitution. Say that to your folks at the dinner table, make them happy. Okay. The process is a chain reaction. That's why the balloon just exploded at the beginning of this video. Quite exciting, huh? In the propagation step, one radical is produced for each one used. So in initiation, I'll do a slightly different diagram when I do the freehand. This is a good start, warm-up. So we've got chlorine molecule making 2 chlorine radicals. ClCl, Cl2, making Cl dot plus Cl dot. We do say dots, that's just the accepted way of saying it. The single dot is an unpaired electron, 1 electron, and the weakest bond is normally broken. So here are the bond enthalpies. Think of bond enthalpy as how much it's going to cost me in US dollar, Sing dollar, Indian rupee to break this bond. So the 412, that's going to cost me a lot more than the 242. So this ClCl, green, is normally for a halogen. I'm assuming this is for chlorine, is much lower than these. This is a carbon-carbon, that could be a carbon-hydrogen. So what's going to happen? The ClCl bond is going to be broken because it has the lowest bond enthalpy, requires the least energy, and nature will find the path of least resistance. The radical will react with methane to make a methyl radical and hydrogen chloride. The chlorine can then react with a methyl radical to make chloromethane and a chlorine radical. Notice in propagation, radical plus neutral makes radical plus neutral. Neutral plus radical makes neutral plus radical. And we can represent these using the ball and stick model as well. Here's methane with a chlorine radical making a methyl radical plus hydrogen chloride, which is exactly the same as this first equation above. The second one is the methyl radical reacting with chlorine to make chloromethane, and the chlorine radical, which is this one here. They're very reactive. They want to pair up with a single electron, and they do this by abstracting or removing a hydrogen from methane, leaving behind a methyl radical. The termination steps, there are 3 steps, so let's just have a quick look. In initiation, 1 step. Propagation, 2 steps. Termination, 3 steps. 1, 2, 3. For a termination, we have 2 radicals making a neutral molecule. So 2 Cl radicals can collide and make a chlorine. A chlorine radical and a methyl radical can collide and make chloromethane. Or 2 methyl radicals can collide and make ethane. So in the reaction pot, at the end of this reaction, we have a multitude of products. This is why I saw lots of black smoke in the reaction. Removing the radicals brings an end to the reaction, but it's not very likely at the start because of their low concentration. So as the reaction proceeds, you get more and more radicals, hence its chain reaction and explosive nature. So key words, homolytic fission, where you get breaking of a covalent bond, 1 electron going to each of the species to form a radical. This is achieved by shining UV light. ClCl breaks because it's the weakest bond. And with excess chlorine, you can get further substitution and a mixture of chlorinated products. So you can get the mono substituted, the di substituted, tetra substituted, and did we stop? Yes, we did. Try and tetra substitution on to these. You can also get further substitution, which I'll go through on my